In this lecture, we're going to do a problem which was asked in TIFR 2015, which was based on time-independent Schrodinger equation. So if you remember, uh, in time-independent Schrodinger equation, we've studied that the form of the equation is given by h psi is equals to E psi, and here E is a constant. E is a constant and a real constant. And we'd also discussed that it cannot be a complex valued function, rather it has to be a real valued function. We've seen that the solution for these particular time-independent Schrodinger equation are also called as the stationary states. These are called as the stationary states. These are called as the stationary states. And if we really want to find why these are called the stationary states, we have seen that if I measure Hk over this psi, I get a definite energy, which is E psi. And this definite energy is like constant energy. And on this concept, the people have asked the question in TIFR 2015. We have to utilize this concept, and let us see how we are going to do it. See, question given to us is that a particle is moving in one dimension under a potential Vx, such that for large positive value, Vx is equals to Kx raised to power beta, where K is greater than 1, and beta is greater than equal to 0. Okay. And if the wave function in this region is of the form psi x is equals to exponential minus x raised to power lambda, which of the following is true? So we have to find that if for the large values, means it will also encompass values tending to infinity. Okay. So for large values, we know that our psi x is nothing but exponential minus x raised to power lambda. I'm refraining right now from finding the normalization constant. It's not that required right now. So even if I multiply it with some normalization constant, it's not required because after all, this will be like this. Even if I multiply with some normalization constant, on both sides, this will vanish. So I'm not bothered about it. This E must be a constant. This is something that I already know from time-independent Schrodinger equation. And in fact, you also know that if you want to find what would be H would be simply E. And what would be H square? It would be again psi star H star psi dx, and which is nothing but it is equals to E square integral psi mod whole square dx, and which is simply E square. And we know what is the spread in H. So spread in H is simply H square minus H, like expectation value of H square minus expectation value of H whole squared, and this would be 0, which implies that there is no such spread, or there is no such variance. Okay, so there's no such deviation from the mean. So basically, what you can say, if there is a wave function, then each eigenket will have a definite energy. This is what I want to say. So this definite energy, or the energy being constant after a measurement of Hk, is a special feature of time-independent Schrodinger equation. And that is what we are using here. Hk psi is equal to E psi. And for large values, we know that psi is given by exponential minus x raised to power lambda. So I'll simply do first derivative, which is simply minus lambda x raised to power lambda minus 1 exponential of minus x raised to power lambda. And if I take a second derivative, it will be equals to minus lambda into lambda minus 1 x raised to power lambda minus 2, and minus, I think it will be exponential. If I differentiate, this will turn out to be plus lambda square x raised to power 2 lambda minus 2, and this whole times psi. Okay. So I hope I am not doing it wrong, because if I take the derivative of exponential, it will become exponential, and then minus x raised to power lambda would be minus lambda x raised to power lambda minus 1. I hope it is clear. So I have taken the second derivative, and now I'll use it here. So it will be minus, oh, so sorry about it, minus hk square upon twice m psi double dash plus Vx psi is equals to E psi. And I know already that my psi double dash is in terms of psi only. and psi is a non-zero wave function, so I can remove it. So what I'll get after all is minus h ket square upon twice m lambda square x raised to power 2 lambda minus 2 minus lambda into lambda minus 1 x raised to power lambda minus 2 plus kx beta is equals to e. And this is a constant, by the way. Okay. So now let's just take a highest power common out. So what I'll get, I will simply get x raised to power 2 lambda minus 2, and inside I'll get minus h ket square upon, like this will be minus h ket square lambda square, sorry, lambda square upon twice m, and plus h ket square lambda into lambda minus 1 divided by 2m, and this will be 1 upon simply x raised to power lambda. Okay, plus k, if I take in this completely common out, okay, x raised to power beta minus 2 lambda plus 2 is equals to e. Okay, so what do you want? I mean, what should I do? I would want somehow that this should be a constant. I mean, this particular thing should be free from x. This particular thing should be free from x. It should be free from x. Okay, so this is my first requirement, that this particular thing should be free from x. What should I do? I should rather place this particular thing there itself. So I'll write e raised to power e into x raised to power 2 minus 2 lambda. Okay, e x raised to power 2 minus 2 lambda here, and here I'm getting minus h ket square lambda square upon twice m plus h ket square lambda into lambda minus 1 upon twice m and 1 upon x raised to power lambda plus k times x raised to power beta minus 2 lambda plus 2. Now what will happen is that we are considering it for the large values of x only. Okay, so we are considering it for large values of x, which also implies indirectly that I can take limit x tends to infinity on both sides. So let me take x tends to infinity. Now I'll have to consider option by option. Okay, so let me first consider the first option. What is the first option? First option was, I think I'll have to see what is the first option. First option is lambda is equal to beta by 2 plus 1. And by the way, this is the only option which is said to be correct. Beta by 2 plus 1. Okay, so let me check, because there's no other way out. I mean, okay, now see, I already know what? I already know that beta is greater than equal to 1, which implies that lambda is greater than equal to 3 by 2, and which implies that minus 2 lambda would be less than equal to minus 3, and which implies 2 minus 2 lambda would be certainly less than minus 1. So it implies that this power is negative. This power is negative. Okay, this power is negative, which implies what? Which implies that limit x tending to infinity, x raised to power 2 minus 2 lambda would be simply 0. So as x tends to infinity, my RHS goes towards 0. It implies what? By the consistency of equation, my LHS first thing must be free from x. Must be free from x. Why it should be free from x? Because see, if I had not taken this x there, the first thing was that on the right hand side I had a constant. So initially, if I had not taken it there, because this was here now, so somehow I had to make it easy. So what I have done, I have taken it there. So it should be free from x. Okay, I should not have any term in x. Okay, or in case I have any term in x, then on both sides the power should be same. Okay, on both sides power should be same. What I mean is that if I have something in x raised to power beta here, so I mean, this is what I want to say. I mean, as x tends to infinity, since here you do not have anything now, because your RHS goes towards 0. Now LHS should be free from x, and rather it should be 0. Rather it must be 0 according to given scenario. Okay, according to given scenario, because being free from x was a possibility only till this end. But now here what I did was, actually I knew that if this remains then it will be a little bit difficult for me to process. Okay, it will be a little bit difficult for me to process because see, in any case, uh, see, it will be free from x only if this becomes 0 and this becomes 0 simultaneously. If this becomes 0, then lambda should be equal to 1. Okay. And if this becomes 0, then lambda should be greater than equal to 3/2. I mean, so this will be a little bit difficult from here to judge. So therefore, I have just taken this on the right hand side. Okay. So I should not write free from x, must be rather 0. That would be working. Okay. That would be working. Okay. Must be rather 0. Now, if it is 0, it implies that LHS should be 0. Now see, as x tends to infinity, I know 1 upon x raised to power lambda would be 0 because lambda is already positive. So this will go towards 0. It implies what? It implies that my k x raised to power, I think what was that? My k x raised to power beta minus 2 lambda plus 2 minus hk square 2 square lambda square upon twice n. This must be 0. Now see, in order that this must be 0, now I'm taking 2 to 3 cases. If beta minus 2 lambda plus 2 is strictly greater than 0, that is, what should I write? That is 2 lambda is less than beta plus 2, that is lambda, if it is less than beta by 2 plus 1, okay, then what will happen? Then I know that beta minus 2 lambda plus 2 would be greater than 0, and which implies that x raised to power beta minus 2 lambda plus 2, limit x tends to infinity, it will go towards infinity. If beta minus 2 lambda plus 2 is positive, then x raised to power beta minus 2 lambda plus 2 would be tending to infinity as x tends to infinity. So lambda cannot be less than beta by 2 plus 1. If I'm writing lambda is, if lambda is less than, if beta minus 2 lambda plus 2 is less than 0, it implies what? It implies that lambda is greater than beta by 2 plus 1, which implies what? As x tends to infinity, your LHS will only have this particular factor, that is minus hk square lambda square upon twice n, and which certainly is not 0. So beta cannot be greater than lambda cannot be greater than beta by 2 plus 1. Lambda cannot be less than beta by 2 plus 1. It implies that one possibility is left, that lambda should be beta by 2 plus 1. If lambda is equal to beta by 2 plus 1, then your LHS is free from x. First thing, LHS is free from x. So it is only a constant here. Okay. So as x tends to infinity, your LHS will remain free from x if lambda is equal to beta by 2 plus 1. So even as x tends to infinity, your LHS will not have any term in x. Okay. Now what will happen? So as x, now what we want is that as x tends to infinity, our LHS should go towards 0. So what does it imply? It implies that now beta minus 2 lambda plus 2 should be equal to 0, and your this k should be equals to hk square lambda square upon x. However, this was not asked in the examination, but this should be another condition. Otherwise, there would be no consistency. However, the only relation between lambda and beta was asked. So lambda should be equals to what? Beta by 2 plus 1. I hope this solves your problem. Meanwhile, I will recommend you to watch all the lessons that we are preparing right now on quantum mechanics. It is going to be a lengthy series, but I am sure that it is going to really be very fruitful for your any of the examinations that you are fighting for, be it your IIT exam, be it your NET exam, GATE exam, TIFR, just anything. So I hope you are going to stay continued with this channel. Till then, take care. Bye-bye.